In this video, we are going to look at the molar mass of a gas and figure out how we can calculate things like the mass of a gas that's formed instead of just moles, especially if it's gas that we might not know of or an unknown gas. So remember, when we're dealing with molar mass of a gas, our N is moles. We can also use the fact that the molar mass is grams per mole. So we can say that N is equal to the mass divided by the molar mass. Because if we look at the units of this, we would get grams over grams per mole. So my grams would cancel out. My moles are in the denominator of the denominator. So it really hangs out in the numerator. So my units would just be moles. So if we plug that in for our ideal gas law, we have PV is equal to mass in grams over molar mass in grams per mole times RT. So all I did was take PV equals nRT and substitute mass over molar mass in for N. We can rearrange this to solve for the molar mass. And when we do that, our molar mass is going to be equal to the mass times RT over PV. So we can use the ideal gas law to solve for an amount in moles and use that in stoichiometry problems involving gas phase reactants or products. Let's look at an example of that. Sodium azide, which we looked at before, is responsible for the inflation of an airbag. And if you don't have this in your airbag, then the airbag will not detonate. So we can calculate how many liters of nitrogen gas would be produced at 1 atmosphere and 25 degrees Celsius from 37 grams of sodium azide. What I want you to really be aware of is if you're using the ideal gas law, is only for gases. So I can't calculate the moles of sodium azide and plug that into the ideal gas law because sodium azide is a solid. So what I can do is calculate the number of moles of sodium azide, use my mole to mole ratio to solve for the moles of nitrogen, and then plug that into the ideal gas law. So I'm going to start with my 37.0 grams of sodium azide and multiply that by the molar mass. Go ahead and get your calculator out and multiply the molar mass. All right, what do you get? I get 65.0 0.011 grams of sodium azide. So now my grams cancel out and I have moles of sodium azide, which is great because I can use the mole to mole ratio. In this problem, I am only concerned about the things that it's asking for. So it is dealing with nitrogen gas, and we're given sodium azide. So those are the only two components of this reaction that I'm going to look at for this problem. I know that I have to have moles of sodium azide on the bottom. So we will take 2 moles of our sodium azide, and the coefficient for nitrogen is 3. So it's going to be 3 moles of nitrogen. Now this gives me the moles of nitrogen. So you can take this and plug it into your calculator, multiply 37 by 3, get that answer, then divide it by 65 times 2. And when you do that, you should get 0.854 moles of N2. Nitrogen is a gas, so I can use that in the ideal gas law. Sodium azide is not a gas, so I cannot use it in the ideal gas law, right? Solids don't have pressures in the same way that gases do. The solid particles are not moving around and hitting the side of the container. Now, nitrogen is a gas. So we can use the ideal gas law. We can use the ideal gas law if we're dealing with moles of nitrogen. So I cannot stop at moles of sodium azide and plug it into Pivner because that's not a gas. Now I can see what all of my numbers mean. Pressure is 1 atmosphere. Temperature is 25 degrees Celsius. Yep, you got it. We have to change that into Kelvin. So we have 298 Kelvin, and then our N is what we just calculated, 0.854 moles of nitrogen. And this is asking us to solve for liters. So V is what we're looking for. So I can use this to solve for the volume. When I rearrange Pivnert for volume, I get V is equal to nRT over P. And we have our plug and chug situation. So our moles is 0.854 times R, 0.0821 liters times atmospheres over moles times Kelvin. And then we can multiply that by our temperature, which is 298 Kelvin. And then we will divide that by the pressure, which is 1. So when you plug this into your calculator, you will multiply your moles, 0.854, times our gas constant, 0.0821, and finally times our temperature. And when I put that in my calculator, I get 20.9 liters.